So, welcome everyone. Today we have Hersh Singh from Fermilab, who will tell us about fermionic anomalies on the lattice.
Okay. Thank you. Thank you for having me. It's been a great pleasure meeting people. I set my like a 1 hour, right?
Wow, yeah.
Okay, so today I want to discuss a problem that's interestingly plagued, let's say, quantum field theory and standard model for a while, and there's been lots of interesting progress, and yet the problem is sort of unsolved. So I kind of want to go over it and talk about some of the recent progress in that direction. So the story starts with the fact that we all know, which is that the standard model of particle physics, it's an enormously successful theory, right? Has made amazing predictions that are tested to tens of decimal places, and we really believe in it. However, it has a very rather weird, embarrassing problem. And the problem is that it's a chiral gauge theory. And that by itself is not the problem, it's a feature of the standard model. The problem is that we don't know how to formulate a chiral gauge theory for computer simulation. We don't know how to do computer simulations of a chiral gauge theory. And you may be tempted to say that that's kind of a technical problem about algorithms or hardware or something like that. But what I want to argue is that that's not the case. The fact that we don't know how to do computer simulations really means that we do not know how to define the standard model in a non-perturbative way. In other words, there is no known non-perturbative lattice construction of the standard model. In general, there is no known non-perturbative lattice construction of a non-abelian chiral gauge theory in 4 dimensions. Okay, so that's the problem. Now, to kind of maybe get to where that problem how that problem comes about, let's just recall a Dirac fermion in 4 dimensions or any even dimensions, right? Just kind of see what the setting is. So if you have if you just take a Dirac fermion, a free Dirac fermion with an action that looks like that, it has the psi. So this is all Euclidean signature. Most of my talk will be Euclidean. There's a field psi which has this U1 vector symmetry, right? That's just e to the I theta. There's a U1 chiral symmetry with a gamma 5 up here. The fact that there's a gamma 5 means that you can define left-handed and right-handed wild fermions. So you can define these projectors, 1 plus minus gamma 5, and then those are your wild fermions, right? Now, the problem is that naive attempts to take this Dirac fermion and put it on the lattice. So that means put the theory on a space-time lattice such that you can take a controlled continuum limit with no perturbation theory involved at any point in the process, right? So that would be a non-perturbative way to define this theory. If you naively try to discretize this theory and put it on a lattice, what you get what people call doublers. Okay, so what does that mean? So just to see what the problem is, let's look at 2 dimensions. We can choose the basis where gamma 1 and gamma 2 are sigma 1 and sigma 2, and gamma 5 is sigma 3 in that basis. So that's diagonal. The Dirac operator then just looks like sigma 1 d1, sigma 2 d2, right? And if you write down what the action is, the Dirac operator in momentum space has this form. It's off diagonal. And you can kind of expand it out, and you see that the psi fields in the basis in which gamma 5 is diagonal, psi, the 2 components of psi are just the right and left-handed wild fermions. And if you just expand it out, you get one piece which is the left-handed, and the other one is right-handed, right? And so if you want it in the continuum, you could just if you wanted to study a theory of single wild fermion, you could just throw it away, right? And you would say that's the action of a wild fermion, which is fine in the continuum. Okay. So how do you get a theory on the lattice? Well, one way to do it is to, again, start with the continuum action and then just discretize, do a replacement where you take the, let's say, the derivative operator and replace it by finite differences, right? Now psi i's would be lattice fields, psi x is a continuum field, and this would be a very reasonable lattice approximation of the derivative operator, and becomes exact in the a going to 0 limit where a is my lattice space. So in momentum space, what this looks like is that you have momentum P1 here, but then on the lattice side, this finite difference looks like a sine. Okay, so this P becomes a sine P, and in a going to 0 close to the continuum limit, this of course agrees. But in general on the lattice, this is different, right? Okay, so the lattice action then looks like this, where your Dirac operator is something like this. This is what the theory, a naive theory for a Weil fermion would look like on the lattice. Okay, now let's actually check if that naive assumption is correct. If for this d of p, there's a 0 at when p is 0, so that's good. That is the original Weil fermion that we were looking for. But now it also has additional zeros at the edges or the corners of the Brillouin zone, right? So pi comma 0, 0 comma pi, pi pi. So those are also zeros, which means that they also correspond to particles in the theory. That's not what we wanted. Okay. So it looks like instead of one Weil fermion, we're getting 4 Weil fermions. But maybe you could say, okay, but they're all like the same chirality, so maybe still a chiral theory. That's also actually not the case. If you expand out the Dirac operator close to the various corners, you find that there's, when one of them is pi, the other one is 0, you get a relative negative sign. So if this was a right-handed and this was a right-handed Weil fermion, these two would be left-handed. Okay, so they're moving in the opposite direction. So actually, instead of getting a theory of one Weil fermion, we're getting actually 2 Dirac fermions, completely not what we thought we were going to get. Okay, so this theory is completely vector-like, not a chiral theory. And in general, for 2k dimensions, you get 2 to the d minus 1. So in 4 dimensions, right, you would get 2 to the 3 Dirac fermions. And here we discussed the case of a Weil fermion, but notice that this kind of doubling will happen for actually if you start with a single Dirac fermion as well, because of the same logic. You get the sign, and then it has additional zeros. And in general, if you want to study a theory of a single Dirac fermion in 4 dimensions, you'd get actually 16 Dirac fermions in 4 dimensions, right? So this is the thing, that this is what is called the fermion doubling problem. Now, a very reasonable objection to what I'm saying is that there are infinitely many ways to discretize the free fermion action, right? Can you be clever and avoid this problem? For example, you could have chosen a different discretization of the derivative operator, right? Some higher order thing, or even more clever with some trigonometric functions or something like that. This is where this no-go theorem comes in. Okay, so Nielsen and Inomiya showed that if you started with a general, completely arbitrary quadratic free fermion action, so the fact that it's quadratic is what I mean by free here, and you impose some very reasonable conditions on what the action should be. So the Dirac operator that comes here, if you want their theory to be local, you want d of p to be a periodic analytic function of p. If you want to have the right continuum limit, it has to have for small p, it has to have the same expression as the continuum Dirac operator. Then, if you don't want any doublers, then it has to be invertible everywhere except p equals 0. That's the thing we just saw. Doesn't happen for the naive discretization. And finally, you would require, if you require the theory to have an exact chiral symmetry, you want the gamma 5 to anti-commute with d. Okay, and what Nielsen and Inomiya showed is that these 4 conditions cannot hold simultaneously, which means you cannot be more clever with the discretization, at least if you want all of these very reasonable looking conditions to be true. Okay, so that seems kind of like that seems like a problem, right? Like if you believe that the standard model exists as a theory, as a continuum quantum field theory, you'd like to be able to define it non-perturbatively. But here the problem looks much more severe. We're talking about a free Dirac fermion. So here at least it should be solvable in some way, right? We know that a free fermion should be doable on the lattice. Okay, so the point is, what Nielsen and Inomia are saying is that you have to violate one of these conditions, right? That has to happen if you want to get a lattice theory for a single Dirac fermion with no doublers. So then the question becomes, okay, which one? That again seems like now a technical kind of problem. Maybe you have to violate it, and then you can get a theory with a single Dirac fermion. So one of the first things that Wilson suggested. When he came up with lattice gauge series, he I think was already aware of this problem, and this was one of the first suggestions. What you can do is you can add a momentum dependent mass term to the theory. So this is the naive discretization, which is now what you do is you add a mass term which does the following. So this is the dispersion relation. This is E squared in a way, and this is the 0 at the origin, which is good. That's what we want. And then this is the one at pi, which is the one we don't want. So what you can do is add a mass term, which doesn't do anything here, doesn't change the low energy physics of this Dirac fermion, but makes this one massive. And once this is massive, then at low energies you can make this mass as big as you want. And at low energies you have just a single massless particle. Okay. So this is fine, right? Like this you can do. It's totally legitimate, and you will get the right continuum limit. But the problem here is that you've added a mass term at the lattice level. So at the lattice level, you have broken the chiral symmetry. In the continuum limit, you are getting the right theory, but at the lattice level, you've broken the symmetry. And that symmetry, it's nice for theoretical reasons because it lets you prove things like let's say that there's no additive mass renormalization and things like that, if you have this exact chiral symmetry protecting you. And it's also kind of, if you break some symmetry at the lattice level, it also obscures the physics of that symmetry in a way, right? So you would like something better, but just to kind of highlight what goes wrong then in the Nielsen-Inomia is that now Wilson's idea breaks this symmetry, right? You're getting all of these things, so you have to break them. So that's what what is called Wilson fermions. As I said, it's a totally legitimate way to do it, and people in lattice QCD simulations do also use Wilson fermions when they don't particularly care too much about the chiral symmetry or preserving it in the continuum. Okay, so then the question is, of course, there's many ways to do this. That was just one idea. So is there an optimal? Is there a best way to do it? This is, in a way, the question that Ginsparg and Wilson asked in '82. And they kind of made this following observation. They said, okay, of course, the continuum theory has an exact chiral symmetry. We know that. But the lattice theory doesn't seem to. So what happens if you start from a continuum theory and then construct a lattice theory from that by doing some kind of renormalization group blocking type of procedure? Okay, what happens to the chiral symmetry? So the picture is that you start with a continuum theory and you kind of superimpose a lattice on top of it, and then you replace fields. You kind of put fields at each of these blocks by kind of some kind of average over this block, right? And there's kind of a systematic way to do it, and you can get a lattice theory from that, right? So what Ginsparg and Wilson found is that if the continuum Dirac operator, so gamma bar here is just gamma 5 in arbitrary even dimensions. If the statement of exact chiral symmetry for the continuum Dirac operator, it's that these two anti-commute, then on the lattice what they found was that the right-hand side is not 0 anymore. It is, in fact, broken. This chiral symmetry is broken, but it's broken in this very specific way. Sorry, this should not be, these should be the same font. Okay, so this thing is called the Ginsparg-Wilson relation, which says that the chiral symmetry is broken in this specific way. Of course, in the which A is the lattice spacing. So when A goes to 0, you're getting this exact chiral symmetry again. But it's doing something more. Okay.
That left D is also, that's not D slash, that's D. What?
Oh, yeah, thank you. So I am, this is my notation. So when I'm writing this D, it's like, it means D slash. Yeah,
Okay,
so both of these are supposed to be D slash.
so that's D slash and the thing in the box is,
Okay, these should be the same font, that's.
but which one? There should be the,
Oh, this should be, okay, so this upright D is what I'm using for lattice D. And the curly D is what I'm using for the continuum D, but they're both supposed to be D slashes. Yeah. Thank you.
Sorry, you told us that like adding the mass, we also break chiral symmetry.
Yes.
It breaks in the same way or not?
Yeah, that's a great question. And it, that is exactly what I'm coming to. Yeah, good. So this is also looking like it's breaking the chiral symmetry. But the interesting thing is that there's more structure here in the way it's breaking it. And that's kind of where all the interesting stuff is. So that's what I will talk about in a minute. So it's a better breaking in a way than what Wilson fermion does. Okay, so this is exactly why. So why is this interesting? Okay, so one of the consequences of breaking the symmetry in this way, which is the Ginsparg-Wilson relation, is even though you don't have the chiral symmetry that you thought you wanted, you actually have a different chiral symmetry. So Lucier in '98 showed the following. If you take now a lattice action with this D, where this D is a lattice D, which satisfies the Ginsparg-Wilson relation, then you have an exact symmetry, which looks like the following. So if you take the infinitesimal transformation D psi to be gamma 5 psi, if it's just a gamma 5, then it's the normal chiral symmetry. But here we're defining a gamma 5 hat. So there's a modified gamma 5 hat, which is defined in the following way. You take gamma 5 hat and you multiply it with a operator which depends on the Dirac operator itself. Okay? So what this is doing is it's kind of defining a slightly non-local version of gamma 5. Okay, so that's the gamma 5 hat. Now if you use this gamma 5 hat to define this chiral transformation, and what you know, you just kind of take the action, you look at the variation, you plug these in. What you find is that the variation is exactly given by this kind of expression, and that's exactly the Ginsparg-Wilson equation. Okay, so if D satisfies the Ginsparg-Wilson equation, then this modified symmetry is an exact symmetry of the action. Okay, again, in the A going to 0 limit, this looks very much like the continuum chiral symmetry, but with a non-zero A, it's like some non-local or slightly non-local version of it. But it does the exact same job on the lattice as the continuum chiral symmetry. Okay, so it seems to capture, so for example, it again will like in the presence of gauge fields, right? Ultimately, you want to gauge these the U1 symmetry here, and in the presence of gauge fields now, the presence of this symmetry, even though the usual chiral symmetry is broken, is enough to ensure that the fermions will remain massless. You will not get an additive mass normalization, which in lattice QCD calculations is kind of annoying because that means every time you change your lattice spacing, you have to again tune the parameters such that the fermions stay massless. But in this case, you don't have to do it. Once the fermions will stay exactly massless on the lattice, even in the presence of gauge.
Is it a U1 symmetry?
Yeah, so in this case, I am talking about a U1 symmetry. Yeah, this is all we can just. Good. Although there is some there is a question of whether or not this is a compact U1 or maybe a non-compact U1. That is an interesting question, and maybe I'll comment it in the end. But that's also fair point. Okay, so at this point, you can raise the following very reasonable objection. The chiral symmetry, famously, is involved in an anomaly in 4 dimensions, right? So the free meaning no gauge fields four-dimensional Dirac fermion has a global, exact global chiral symmetry, right? Which is completely fine. But the moment you turn on gauge fields, that symmetry, so if you turn on a gauge field with the U1 symmetry, that chiral symmetry is broken, right? That's the statement of the anomaly. So in other words, there's a mixed anomaly between the U1 vector symmetry and the U1 axial symmetry. So you gauge U1 vector, you should break U1 axial. Okay, so this is the thing that's famously computed by this triangle diagram. Now, if the lattice action, as we saw, is invariant under the chiral symmetry, and that stays to be the case even when you turn on gauge fields, then where does the anomaly come from, right? It should be broken. So historically, in the community, there had always been this lore that there are no anomalies in the lattice because the anomalies somehow involve it's infinite degrees of freedom or some complicated thing with the measure or something, and so you don't really get the anomalies. You don't really get anomalies on the lattice. Okay? And this was the way in which you can understand fermion doubling, because if a lattice theory cannot reproduce anomalies, then something must happen to sort of cancel the anomaly, and that's the origin of fermion doubling. From this point of view, right? Fermion doubling occurs because the lattice theory tries to cancel the anomaly. And the way it can do it is by adding additional fermions such that the anomaly cancels. Okay, so that is indeed true. But there are some interesting caveats. So this is the lore, right? But now we're saying that, of course, we are getting a single Dirac fermion, and that we have no doublers, and we're saying that we have a chiral symmetry. So what's happening? Okay. So what's happening is that if you just actually look at the Jacobian, right? Like this is now very analogous to how we would look at it in the continuum formalism. If the action is invariant, the only place the anomaly can come from is the Jacobian. And indeed, with this modified symmetry transformation, if you compute what the Jacobian is, you will get a trace of this gamma 5 hat. Okay? And it's the hat that has a non-trivial trace. The regular gamma 5 is the trace 0. But then the hatted version of it has the same as trace gamma 5t, but then that's exactly the index of t, because it will have it will count the positive and negative 0 modes with the right sign. Okay. So actually what's happening is that you're just getting the anomaly exactly on the lattice, just by looking at the Jacobian in a very simple way. Once you've identified the symmetry, the anomaly is just completely trivial in this formalism, which is pretty subtle in the traditional continuum way of looking at it. Okay, so that's right. That's a real kind of signal that this formalism is capturing something essential, because it's capturing the anomaly on the lattice, which really, I think before this was considered impossible, that a lattice series don't, and many people even in the community to this day think that that is the case. Okay, let's just a little bit. Okay, but of course, in recent years now, there's a lot more new examples of anomalies getting captured on the lattice, exactly. So, okay. Yeah, this is like. So again, the naive argument was that doubling occurs because our lattice cannot reproduce the anomaly. The Ginsparg-Wilson relation says that we can capture the anomaly. So therefore, if there is a Dirac operator which actually satisfies the Ginsparg-Wilson equation, then we can expect that it doesn't have this doubling problem, right? So then the question is there actually, like so far I've not said anything about whether there is a solution to the Ginsparg-Wilson equation. I've said that there is this Ginsparg-Wilson relation, which seems pretty cool, but is there a solution? So this is kind of where there's this interesting history. So this is like just a citations per year chart of this paper by Ginsparg and Wilson from '81. So you see that they wrote this paper, and this paper was just completely forgotten. It has 0 citations for about like 15 years or something like that, right? And I think 81 is also the year, or 81 or 82 is the year that Wilson got the Nobel Prize. It's not like these people are like unknown people who are just writing some paper. So this paper was completely forgotten for a long time, and then suddenly something happened, and now it has like over 1,000 citations or something. So what happened in 97 was exactly the discovery of a solution to the equation. So Ginsparg-Wilson wrote down this equation, but didn't really know how to solve it. So it kind of just like sat there for many, many years. And then through a sort of a very serendipitous kind of discovery, many people, starting with Peter Hasenfratz, discovered that some particular form of lattice actions that they had been working on, called fixed point actions, they actually exactly satisfied the Ginsparg-Wilson equation. And then once Peter Hasenfratz discovered or rediscovered this thing, it was discovered that there's another formulation called the overlap formulation. You know, that also satisfies this. And then it was also realized that another formulation called domain wall fermions, David Kaplan also realized the Ginsparg-Wilson equation. And so all of these formulations that people had worked on from different perspectives, with the goal of getting the chiral symmetry right, all converged. They look very different, but they all have in common the fact that they satisfy the Ginsparg-Wilson equation. So that is that's kind of the final result in a sense by Lucian, which I mentioned, where this Ginsparg-Wilson equation satisfies an exact or modified chiral symmetry on the lattice that unifies all these approaches together, right? That's the essential thing. Okay, so just to kind of give a sense of what does it mean to satisfy the Ginsparg-Wilson equation, what does the solution look like? So one way of thinking about it is if you just kind of write a Dirac operator in this form, h over h plus 1, and you plug this in, what you find is that in this form, the Ginsparg-Wilson equation implies for this h that it has this exact chiral symmetry, right? So you can take h to be any operator that satisfies the exact chiral symmetry. Well, of course, on the lattice, we don't know how to do that, and that is the problem. But let's just, we do know in the continuum in H, which is the continuum Dirac operator, right? The D slash. What happens if I just put that in? Okay. So if I put that in, I get a Dirac operator which looks like this, which by construction satisfies the Ginsparg-Wilson equation. Okay. But this is actually just a polyvillars regulated Dirac fermion. This is exactly what you would get from a boson, bosonic field with the same, with a massive bosonic field with the same kinetic term as a fermion. Okay. So from this point of view, a polyvillars regulated Dirac fermion is actually a solution to the Ginsparg-Wilson equation. But it's not totally fair to say that because it has a continuum perturbative regularization, the polyvillars regularization, whereas what we really want is a non-perturbative lattice regularization. However, this is quite instructive, and this is what you were trying to get to in a lattice point of view, and you can even understand how the symmetry, like the Lucier symmetry that I mentioned, that kind of acts in this way, and that acts just by saying that the fermion transforms, but the boson doesn't, right? That's the kind of symmetry that you're looking for, and that would be the exact analog of a Lucier symmetry from this point of view. Okay, so the question of how to get that on the lattice, how to get like a nice closed form solution, like the polyvillars one, it's kind of solved finally by what is called the overlap operator. We don't really have to get into the details of how the overlap operator is constructed, but I think I just want to maybe emphasize that you can think of the overlap operator as providing a non-perturbative lattice construction of the polyvillars regularization that they could do. Okay? And then once you have an explicit construction, you can show that there is no Dopplers, but because you have the explicit construction, you can just check it. So that kind of solves this problem in a way. The overlap operator and the Ginsparg-Wilson equation I would say totally satisfactorily solve this problem of how to get the anomaly right on the lattice and how to get a theory of a single Dirac fermion on the lattice without any doubler.
Can you go back to the previous slide?
Yes.
So the denominator never is zero in these kind of formulas?
This denominator?
Well, the d slash plus m.
Yeah, because so in my convention, I'm taking gammas to be Hermitian. So d slash is anti-Hermitian. M is so these eigenvalues are imaginary, m is real. So they don't really this never gets
Never zero. But it is infinitely non-local, because you have momentum in the denominator. So like the lattice kinetic term does not have bounded support.
yeah, it does have bounded support, but you can show it's exponential. The decay is exponential. So
Why is it exponential? How do you do that?
I think the way to maybe the easiest way to see it is that this is still an analytic function, and so the Fourier transform or like in momentum space, it's still this still would be an analytic function, so that it should have a exponential decay, right? It couldn't be if it was power law, you would expect this to have some kind of non-analyticity. So that's one way of seeing it. I think the harder question is, and so also like this scale, right? This m sets the scale of how fast that decays. So if you make the mass of the boson really, really large, then it's a much faster decay. I think the harder question is what happens in the presence of gauge fields. And I think that requires a more sort of rigorous, careful argument. And again, yeah, I don't want to say too much about polymers because after all, it is a perturbative regulator, so I don't know ultimately what it means to like define it properly. But for the overlap operator, it has been shown under certain smoothness criteria of gauge fields that it's exponentially local. Yeah, so overlap operator is difficult. I think this here it's mostly just a analyticity argument to say that it must be exponential. Okay, thank you. So good. So this is sort of the summary. We started with kind of trying to get a lattice theory of a Dirac fermion. We noted that there is an exact chiral symmetry for the massless theory. On the lattice, we found that the optimal way of doing it was to replace the right-hand side of this anti-commutator. Instead of being zero, you require this to be this kind of specific structure. And with this relation, you can show that there is actually an exact chiral symmetry modified on the lattice, and that you get the exact anomaly on the lattice as well. Okay, so maybe just to close this thread, at this point, you can ask, like you have now a nice formulation of a lattice chiral symmetry. So if you use this modified gamma 5, maybe you can define now these modified wild fermions using these modified projectors. And if you do that, can you use that as a starting point for construction of a chiral gauge theory? Because now you have these wild fermions with this modified symmetry. And if you can show that when the anomaly cancels, this results in a consistent lattice theory, then you would have essentially solved the problem of chiral gauge theories. Okay, so that's the question that Lucia considered, and what he showed was that indeed a non-perturbative construction can be achieved along these lines for abelian chiral gauge theories. And then since and exactly you can see that that is consistent exactly when the perturbative anomalies cancel, right? So this now can be seen on the lattice in this formalism.
Abelian chiral gauge theory, we usually don't think of as having a UV fixed point. What does the statement mean?
Why do you say that?
Is Landau fault?
Yeah, but that's true for just like a Dirac fermion, right? Is that true for
Any charge matter.
but how do we know that? I think that's the question, right? The whole point is that that would be a perturbative statement, right? Landau pole is a perturbative statement, right? To really say that a theory doesn't exist, you would have to start from a non-perturbative statement, right?
What
And
are
in
the
fact,
continuum
that's also
limits?
true for the.
What are the continuum limits of those supposed theories?
No, but that's the thing. So that is the next question, right? So the way you would do it is it's fine as a low energy theory, right? Now the question of whether or not it has a continuum limit, you can rigorously probe using a lattice construction, right? So you would start with the lattice construction, which you know has the right low energy physics, and then you would look for the continuum limit of that theory. If you can find a continuum limit, that can happen even in the presence of Landau pole. Right? Landau pole just says that the perturbation theory is failing. Okay? But it can happen that the theory finds another strongly coupled fixed point to be in the UV limit. Right? That's not disallowed by the presence of a Landau pole. So it hit, like in the case of just QED lattice. People have looked for a continuum limit and they have not found it, right, in 4 dimensions. So indeed, then there the sort of the prediction of the Landau pole, I think, is consistent with what people find on the lattice, is that the continuum limit doesn't exist. But I think that's not, you don't really know that, right, from a perturbation theory point of view. Having said that, this construction doesn't actually still let you answer that question because we don't really know how to do numerical calculations. So this construction is very formal and and it's sort of infinite volume. To actually, I would say, even though the construction of abelian chiral gauge series on the lattice is solved, a practical construction is still an unsolved problem. Nobody's been able to actually do any numerics with that kind of formulas. So that is maybe precisely the sort of question that you would like to test on the lattice, but we still don't know how to do that. Okay, so then the question, of course, of non-abelian gauge series, right? There's some progress on this approach, but generally speaking, the question for non-abelian gauge series is open, right? We don't know. We don't have a non-perturbative lattice construction for chiral gauge series. Also, by the way, you could do this in 2 dimensions also, right? 2 dimensions, I think there's no Landau pole. You can have abelian chiral gauge series. So that would be another way of saying this. Okay, so there have been many recent attempts in the last year or 2 to get to this. There has been sort of, I would say, some resurgence in activity. But yeah, the problem still is open. There's many interesting proposals. And I will not get to any of these proposals, but I will point out that but most of them are relying on this connection to the bulk boundary correspondence in condensed matter physics. So, in other words, we have a lattice theory, right, which realizes a Dirac fermion with a 2-Ft anomaly exactly on the lattice, which of course implies that the massless nature of the fermion is robust, right? You have as long as you have the anomaly, you will have this massless fermion. But there's another way of getting massless fermions, where the masslessness is robust, and that is by going in 1 higher dimension. Okay, so this is the idea of bulk boundary correspondence, where if you want to do a theory in d dimensions, you go to d+1 dimensions, and you consider an SP symmetry protected topological phase. And the correspondence says that for at the boundary of SPT phases, you get theories which have 2-Ft anomalies, right? So there's a 1-to-1 correspondence between SPT phases and a 2-Ft anomaly. In our case, that means if you have a massive Dirac fermion in the bulk, and you tune the parameters right, what you will get at the boundary of it, you will get a massless chiral fermion. Okay, so that's the essence of this idea called domain wall fermions. due to David Kaplan. The idea that is also still routinely used in lattice QCD is that if you go to a higher dimension and you consider a massive Dirac fermion with a mass profile, so you can put a negative mass on one half space and positive mass on the other half space. What you find, so this is just like even a classical calculation shows you that there's going to be a massless fermion stuck to the boundary, okay, to the interface. And this idea, this originally in the continuum was proposed by Callan and Harvey, where they gave a nice physical picture how the anomaly of this is arising. Right, the anomaly of the boundary is arising by the non-invariance of the bulk under that symmetry with the boundary, and that non-invariance of the bulk theory exactly cancels the anomaly of the boundary theory, and this is the idea called anomaly inflow. The domain wall fermions can be thought of as a lattice instantiation of anomaly inflow. Okay, and it's very useful. Like it's actually practically pretty nice. Okay, so the point is that for there's this one-to-one correspondence between SPT phases in the bulk and anomalies at the boundary. Okay, this is a very, very general statement. For SPT phases, it's very easy, even on the lattice, to take a Hamiltonian with an SPT phase, and then the moment you put it on a boundary, you will get some edge modes, right? That is domain wall fermion. So getting this exactly, this correspondence is very easy. On the other hand, we are also saying that it seems like anomalies, which is you think of as like a continuum formal thing, are exactly realized by Ginsparg-Wilson fermions, right? Like this is, or at least for the case of chiral symmetry, we've seen that so far. So if the Ginsparg-Wilson relation seems to capture, and finally, it has been shown on the lattice that domain wall fermions, the low energy physics, the low energy effective theory for domain wall fermion also satisfies a Ginsparg-Wilson relation, right? So this correspondence is direct, this correspondence is direct, this correspondence is direct. This we've seen one example of. Okay, so the question is then, are there just Ginsparg-Wilson relations for all fermionic anomalies or all fermionic SPT phases to realize them on the lattice? Can you just generically do this always? Okay, to get to that, let's look at a very famous example that comes up in condensed matter physics a lot. This is the Kitaev chain. The Kitaev chain is a 1+1 dimensional Hamiltonian system, which has Majorana fermions at the boundary. So the Hamiltonian, so now we're in the Hamiltonian formulation. Because that's just how the description, the traditional description of the Kitaev chain is. So what you have is again a 1+1 dimension chain of where each side has a single dimensional, so a one component Majorana fermion. And the Hamiltonian is just the nearest neighbor Hamiltonian. Lambdas are your Majorana fermions. The only thing is that you make the strength of these couplings, nearest neighbor couplings, you stagger them, right? So there's these blue bonds and the red bonds. Now, in one limit, if you change alpha, which is the strength of the staggering, you can go at a point where, let's say alpha is 1. Let's say that's the case when all the red bonds disappear. So then you have this kind of picture where all of these neighbors are paired up, right? And we are imagining that this system has a boundary. Okay, so this is just an open chain. On the other hand, if you look at the other limit of alpha -1, where all the red bonds exist but the blue bonds disappear, then everything in the internal in the bulk, they are paired up in the exact same way, but you find that there are these isolated Majorana fermions at the boundaries. Okay, so these are 0+1 dimensional Majorana fermions that exist at the boundary of this Hamiltonian in 1+1. Right? This is what we call a non-trivial SPT phase, and this is what is called a trivial SPT phase. And And again, this is exactly the same picture as the domain wall fermion I showed you, where the fact that there's just the vacuum outside can be considered as a trivial phase. So if you have an interface of a trivial and a non-trivial SPD phase, you would get some massless modes living at the boundary, right? So the fact that there's this two isolated Majorana fermions at the boundary, two Majorana fermions give you one qubit. So this has a two-dimensional degeneracy in the ground state, in the ground state subspace. Whereas this has a unique ground state, right? Okay. So what is the theory of the 0+1D Majorana fermion? Well, that just looks like this. It's just the simplest thing you can write down in 0+1D. Chi is now a Grassmann variable here, right? So this looks very simple. Does this have an anomaly, right? By the arguments we know of as bulk boundary correspondence, we expect this to have an anomaly. Okay, so it turns out that this does have an anomaly. It's a pretty interesting anomaly involving time reversal and fermion parity symmetries. And this has a Z8 anomaly, which means that to cancel the anomaly, you need 8 copies of this Majorana fermion. So from the point of view of continuum path integrals, this is a pretty subtle anomaly. And as far as I'm aware, this was first clearly demonstrated by Witten in his beautiful 2016 article, where he showed that you can get the Z8 by computing an eta invariant on a two-dimensional unorientable manifold, right? So if you look at so it requires some kind of sophistication, I would say, to get the fact that this has a Z8. It's not as simple as computing a perturbative triangle diagram or something. Okay, so the question for us is that can you get this theory on the lattice? And if so, then can you get this very subtle anomaly on the lattice as well? We see that, so on the lattice, sometimes when you can get things right, difficult continuum calculations are pretty simple on the lattice. So if we can get it on the lattice, maybe we will see this in a simpler way as well. So now let's try to construct a lattice, Ginsparg-Wilson lattice formulation, right? Again, by the way, note the following observation. A lattice theory, just in the beginning, we talked about naive discretization. You could just again take dt and then make it into a discrete a difference operator. But then again, you will get a sign and you get a doubler, right? So instead of a 0, instead of getting like a 1D 0+1D 1 Majorana fermion, you get like a doubler in that formula, right? Okay. So actually, it turns out that that obstruction of getting a single Majorana fermion on the lattice still persists if you try to do a Ginsparg-Wilson formulation. And I can talk about this more later, but the technical reason for it is I need to be able to write down a mass term. Okay, and for a single Majorana fermion, I cannot write down a mass term to even start the Ginsparg-Wilson construction. And I can't write down a mass term because there's like chi-square is just 0. It's a single component Grassmann variable, chi-square is 0. There's no, for me, statistics forbid any mass term. Okay, the moment you start with a the moment you have 2 Majorana fermions, you can write down a mass term because I can put down a tau2, which is like an epsilon tensor, to contract to Grassmann variables. Okay, good. So that's the starting point then for the construction of a Ginsparg-Wilson formulation. This has a reflection symmetry where t just goes to minus t, and you can check that this is a symmetry of the kinetic term, but not a symmetry of the mass term. In such a case, if that happens, that's usually a signal that there may be an anomaly. It's not a guarantee, but that sort of hints that there is an anomaly. In this case, of course, we know the answer, that there is a Z8 anomaly. Okay, so again, we kind of go through the process. We say that if you have a continuum action, we would like to get to a lattice action. where D again is some non-local operator, hopefully exponentially non-local, and it would look like this. And you actually can generalize the original derivation of Ginsparg-Wilson in a way to account for these discrete symmetries and Majorana fermions as well. And what you find, if you just like write dr as the reflected D, in the continuum you have dr minus d is 0. That's the continuum relation, of course, that the R is a symmetry. On the lattice, again, you find that the right-hand side is now replaced by something else, right? In the same way that we found earlier for the chiral symmetry. So that's the kind of punchline, is that we can in fact generalize Ginsparg-Wilson relations and the overlap solution to account for discrete symmetries as well in any dimensions for Dirac or Majorana fermion, right? So basically any free fermionic system can in fact be captured in a very neat way with a Ginsparg-Wilson formulation. And the question of anomaly then is the same. How do you get the anomaly? Well, you look at the Jacobian, right? Like, will you find a Jacobian now? So there is an interesting subtlety here, which is that earlier I was talking about Dirac fermions, so I could have taken psi bar and psi to transform independently in Euclidean space, which is what I did. In fact, here you don't have that freedom because it's a single Majorana fermion. So psi bar and psi are not independent in a way, right? They have a Majorana constraint which relates them, and so you have to account for that fact, and that means that in the transformation for this exact modified reflection symmetry, you get now these square roots, which are kind of unavoidable in this. Okay. So that actually is not local now. I think this is not analytic. So here that problem is really there. Like these because these square roots that appear, this now has a power law decay in even in the absence of gauge fields. So, but nevertheless, you can kind of proceed with that, and you find that you then just have the determinant of this matrix, and that will give you actually exactly, if you do the counting right, you find that it gives you -1 to a number, and that number is exactly the mod 2 index over 2 of the Dirac, right? So this mod 2 index anomaly also appears in a very natural way on the lattice by just looking at the Jacobian. So what we're finding is that for 2 Majorana fermions, you're getting this minus sign, right? So that's like a Z4 anomaly. So of this, the final answer is Z8, but the Z4 part of it is what we can get in this formalism. At least if you just look at that Jacobian. Okay, so this is just to sort of summarize the comparison between the known Dirac case and in a sense sort of the new example I showed you was this for this Majorana case, where the symmetry was time reversal or reflection symmetry. The anomaly, interestingly, is not a perturbative anomaly anymore. It's a global anomaly, and yet the way you find it on the lattice is completely the same. It's identical. There's no difference. It's in both cases just a Jacobian. The Ginsparg-Wilson relation has a natural generalization. There's a general sort of modified symmetry, and here you're getting the mod 2 index, and the rest of the things are also the same. That you're getting no Dopplers and no additive master normalizations. Okay, so to summarize, the classic Ginsparg-Wilson relation captures how the anomalous chiral symmetry acts on the lattice in the most optimal way possible. And we can write down a Ginsparg-Wilson relation for global anomalies as well now, which involves symmetries, discrete symmetries such as time reversal, reflection, and Majorana fermions as well. So I think this is what this is sort of saying, is that Ginsparg-Wilson relations are kind of one piece of the puzzle of getting this exact like bulk boundary correspondence on the lattice, right? You're getting a d-dimensional theory by itself on the lattice. with an exact anomaly. But I would say that even though that's very nice, it would be very desirable to also have a Hamiltonian formulation of Ginsparg-Wilson fermions. And there is some work, but I would say that's still not completely satisfactory. And there does seem to be some tension with the other nice properties we want and going to Minkowski signature. That would be, well, I think interesting from a theoretical point of view, but also practically, if you want to do quantum computing and tensor network methods for these kinds of systems, it would be really important to have that. And finally, I mentioned that you're getting in this formalism a Z4 anomaly for instead of the full Z8 anomaly. So that I think is still, or at least I don't understand it, is how to get the full structure of these anomalies, and can you formulate the full correspondence, which I'm not an expert in. I'm sure people here are, but there's a theory of cobordism which is used to then, which is I think the most up-to-date understanding of the fermionic anomalies, and can we just capture all those anomalies on the lattice? So even though we've made significant progress in capturing many fermionic anomalies on the lattice, including global ones, some pieces are still missing. And so the question is whether a complete picture of how fermionic anomalies are realized on the lattice, is this needed to really solve this kind of long-standing open problem of non-abelian chiral gauge series on the lattice? Thank you.
You use the lattice in some way to go further and actually compute Ada invariants.
Yeah. That's a good question. Actually, you can. So that's a very good question, because in a way, so one way to phrase it is that the overlap operator, which is a solution of the Ginsparg-Wilson equation, that actually gives you a lattice regularization of the eta invariant. That's one way of understanding the whole story. And so, yeah, indeed, you can compute eta invariance using that quite straightforward. So, for example, that the relation between the eta invariant and Chern-Simons, in a way that also says that this way you can use the overlap operator to define Chern-Simons series on the lattice as well, for example. So this yeah, there's not that many works on it, but I think this is yeah, it's definitely doable. I think I don't know if many people have had a reason to compute it, compute those things, but it's definitely doable. And I think from the point of view of getting again the full picture, where you like that anomaly can be obtained by computing the eta invariant on RP2 or something. I think you can just compute RP2 eta invariant on RP2 on the lattice in this way. I think that's doable. That would be one way of getting that anomaly, but that's kind of not ideal from my point of view, because you still have to go to one dimension higher and compute the eta invariant one higher dimensions. I think I would like to see that anomaly explicitly in D dimensions and not have to go to D+1 dimensions to see the anomaly.
So when we explain that the anomalies reproduce, the chiral symmetry, global chiral symmetry, gauge symmetry anomaly. So here, this gauge symmetry itself was a vector-like. Yeah. Do you know if the situation like global chiral symmetry, chiral gauge symmetry anomaly, in the case, for example, U1 can be reproduced in the same method?
So you want you talk about a
chiral global, chiral gauge. Probably since you only have U1 example, maybe U1 gauge, but chiral here.
Yeah, so you're saying that if you were to gauge the chiral symmetry, so in the Dirac fermion case, if you were to gauge the chiral symmetry, That's-
U1, for example.
chiral U1,
Yeah, yeah.
will you still get the anomaly?
Yeah, it reproduce anomaly.
I think so, yeah, I think so. I think there's nothing that prevents you from doing it, but maybe we should write it on the board to see. Yeah, you're not talking about a gauge anomaly, right? You're talking about a,
Just the ABG anomaly.
yeah, the ABG, but with chiral
Global
U1.
global chiral, the
Yeah.
chiral gauge.
Yeah,
not
I think that's,
basic
yeah, that you can, yeah,
Uh-huh.
that you can.
Mm. Thank you.
Yeah, yeah, we can see, yeah, there's some subtleties about gauging that chiral symmetry in this formalism is not straightforward, so you have to play more tricks, maybe. But I think you can do that.
Mm.
Yeah.
There are no other questions. Thank the speaker again.